So now that we've derived this important equation for the chemical potential of a component in a solution in terms of the chemical potential of the pure liquid plus RT, the natural log of chi for that component in solution. We derive this from Raoult's law and assuming ideal behavior for both gaseous species and the solution, right? We're now going to put this to use. Okay, so this is a very important equation. We're going to now use it. And one of the things that we want to start to calculate are these thermodynamic properties we've introduced throughout the semester. So the first thing we're going to talk about is, okay, what was the Gibbs energy to actually create the solution? What was the Gibbs energy to produce the mixture? Okay, so that change occurred because we know that after the mixture forms, there's a certain G for the solution, all right, a certain G for the solution that depends on the temperature, the pressure, the number of moles of solution one, or sorry, component one, and the number of moles of component two, right? Remember, deltas are changes, so we made a solution that was like our final state. And what were the initial states? The initial states were the pure species. So I'm going to subtract minus G1, right? And I'm going to even put a star here. So I had pure 1, it went into the solution. G1 star is a function of T, P1, and N1, all right? I also had pure 2 to start with. That's a function of T, P2, and N2, okay? So this is a pretty simple idea. I'm talking about making a mixture. I had pure 1 and pure 2 off, separate from each other to start with. I dumped them together. I made a new state, which was the solution state. The change in Gibbs energy is going to be G for the solution minus G for the pure 1 minus G for pure 2, okay? So with that simple idea now, we go and we say, hold on a second. I just spent a lot of time deriving chemical potential formulas, right? And I know how chemical potential formulas relate to G's, right? We know that G, right, over N is equal to mu, or G is equal to N mu. So we're going to use this idea now to try to make this equation applicable in this scenario, okay? So let's look at G solution first, right? So G solution, well, the solution has two components. All right. The solution has component 1, which has a certain number of moles and a certain chemical potential to be in that solution for component 1. All right. It also has component 2 and a certain chemical potential to be in the solution for component 2. All right. This right here, and I'm just going to kind of write it off to the side, right? This is essentially G solution. I'm going to explain it one more time, all right? If you think about the total G for that solution, you have the chemical potential of each that are contributing to the total G, but how do they contribute? It depends on how much of the actual components are there in that solution. So we have N1 mu1 for solution plus N2 mu2 for solution. That is equal to G for the solution. Okay, so now we have, right, G1 pure that we were subtracting away from this. Well, G1 pure looks like the number of components for that pure situation for component 1 times mu for the pure situation. But the pure situation would be in its liquid state, right? So we had, before here, we had G for component 1 in the pure setting. Well, the pure setting is that liquid state. So we're going to subtract away N1 mu1 star. Via the same logic, right, to make our delta G, sorry, I'll keep using blue. To make our delta G, we're also going to have to subtract away N2 mu2 for the liquid star. Okay? And this term right here from our previous writing that we erased, right, is G2 star. So G solution minus G1 star minus G2 star. pure liquid scenarios ending up in a solution, the delta G for that mixture is this. And then when you analyze it and we look at it, we say, wait a second, I know what these are. Mu1 solution, I have written down here already. We spent a whole sort of lecture working towards that idea. Mu2 solution is the exact same idea, except the subscripts are different, right? This 1 becomes a 2, this 1 becomes a 2, and that 1 becomes a 2. So we can substitute that in and we can see what happens, okay? And let's do that. And we're going to write it all out. All right. So delta G for the mixture is equal to, all right, N1 mu1, okay? So it's going to be N1, all right, mu1 liquid star plus N1 RT natural log of chi1, right? The other part of G solution was N2 times mu2. Well, mu2 is going to be this, but with subscripts of 2. So N2 mu2 for the liquid star plus N2 RT natural log of chi2, right? That's mu for the solution. Now what we have to subtract away is N1 mu1 for the liquid in its pure form minus N2 mu2 for the liquid in its pure form, right? And we can kind of see what happens here, okay? These liquid terms, the pure liquid terms, they're all going to cancel each other out. We have a positive term and a negative term, positive term, negative term. They go away. And so then what we end up with, right? And I'm just going to pull out. So notice this goes away, this goes away, this goes away, this goes away. And I'm going to pull out an RT. So we finally get this delta G for the mixture. And remember, this is for ideal solutions. We're using this, which means we assume ideal behavior and something that follows Raoult's law. Delta G for the mixture looks like RT, right, times N1, the natural log of chi1, plus N2, the natural log of chi2. Okay, so all we did there was factor out the RT, right? But now we're left with an expression that we can go ahead and we can analyze, all right? And remember, this expression for the mixture, delta G, the Gibbs energy change for the formation of the mixture, again, one more time, this evaluation is only applicable for ideal mixtures. But let's look at it and just kind of analyze it quickly. If we look at it, an interesting thing occurs, all right? What we see is that delta G for the mixture, when we have these ideal solutions that are forming, it's definitely going to be negative. Remember, we're doing things under isobaric isothermal conditions. So remember, this is the important delta G. We're under the conditions where it's mapping onto the second law, and so the ideal mixture formation would be spontaneous because we see it has the negative sign. It follows the sign convention we developed earlier in the semester. Now, how do I see it's going to be negative? Remember, R is a positive value. T is always positive because we always make sure it's in Kelvin, okay? Number of moles, those are going to be positive. There's going to be positive, so where does the negative come from? Remember chi. Chi's range from 0 to 1, right? So they're fractions, essentially, right? So inside here, whenever you take the natural log of a decimal, right, what you're going to get is a negative number. So the natural logs inside here force this to be negative. So you might be saying, what happens when I have natural log of 1 and natural log of 0 here? You no longer have a mixture. In all mixtures, these chi's are decimals, and so the natural log of decimal push this as a negative value and this as a negative value, and so then you get a total negative value for delta G, which makes sense because as we mix things and we see them mix, it does occur spontaneously, right? So that's really an interesting idea, but it also lets us quantify this. Now, if I give you a mixture and I tell you the number of moles of certain species, you can go ahead and if the mixture is ideal, all you really need to know to calculate what that negative delta G is the temperature, right? And the number of moles of each species. You go through, you can calculate a value now for these ideal solutions. So it's a pretty powerful tool, right? We can also start to take this result and relate it to other important thermodynamic quantities. So a couple of other things that we've been looking at all semester are things like entropy, right? So what about the entropy change in forming this ideal mixture? Well, we go back and we think about, okay, how does G relate to entropy? And that's a critical question, and it's okay that you don't know how to answer it quite yet. As soon as I point it out, you're going to say, oh yeah, we do know how G's relate to entropy because we have these natural variable relationships that we developed, and one of them said, well, G relates to entropy as the derivative of temperature, all right? So what we can do with this equation is we can say, okay, well, let's apply a change to both sides. Let's apply a delta to both sides. Or think about writing this equation twice and then subtracting it. We did this before, but I'm just going to write it down here. We can turn these actual functions into deltas on each side. And again, think about like writing it twice for two different states and then subtracting them. Or like I said, think about applying a delta to both sides. It'll find the numerator in each case, all right? So now if I want to calculate, right, so this is just a true statement. So if I want to calculate delta mix S, the entropy change for the formation of the mixture, then if I look at this equation, I can take the negative to this side, and then all that this tells me to do is to take the partial derivative of delta mix G with respect to temperature, right? With respect to temperature, right? And then what we'll get, right? Oh, at a constant pressure. And then what we'll get is an equation that we can analyze that gives us the entropy change now, right? For the formation of that binary mixture that we were looking at. So hopefully you can see the math is pretty straightforward. It's a partial, excuse me, it's a partial derivative with respect to temperature. I look down here, and the only really temperature dependent thing that we have here is T itself. So when I take this derivative, right, the T is just going to kind of go away. And so what we get is delta mix S. Once we plug this in there and we do the derivative, we get delta mix S is R N1, oh sorry, negative sign, negative, my fault. We get negative R, because the negative sign comes down, okay? The T goes away through the derivative process. N1 natural log of chi1 plus N2 natural log of chi2. So this then is an equation that we can use to go ahead and analyze now delta S for this mixture, right? And in terms of a sign, we can analyze it again, right? Notice inside here, via the same arguments, this is going to be negative, this is going to be negative, so this whole thing is going to be negative when we analyze it, right? The negative times the negative gives me a value that's positive for delta S mixture, all right? Again, applying our sign convention rules, this makes sense. We'll always have a positive delta XS for the mixture because the disorder is increasing. If I have an ordered system over here that's pure and an ordered system over here that's pure and I dump them together, all right, the disorder increases as you make your mixture, okay? You got all new different molecular interactions forming, you're breaking down the liquid structures, you're adding disorder as you form the mixture. So again, a really interesting example that leads us to some very important, not only just an equation that we can use to calculate a delta S for the situation, but then also it gives us a sign that makes sense for us in terms of our physical understanding of the thermodynamic properties of substances, right? So let's do this for two more species, right? What happens if we ask about a volume change? Now, one thing we didn't get to do a lot of is talk about, you know, changes in volumes and ideal solutions and real solutions and how we can't assume that volumes add. Well, one thing that we're going to show here, all right, is a very important result for ideal solutions. We spent a lot of time in lab talking about how we can't assume that volumes add. Well, what about if the solution was ideal? Well, we know that we have dG dP at a constant T that is equal to V, all right? So via the same thought process as before, I can turn these on the top over here and the top over here into deltas. Again, think about taking this and subtracting it from both sides, making this equation. You end up with these deltas that show up, all right? So now what this tells me is if I want to know delta mix V, all right, what I'm going to have to do is I'm going to have to take a derivative of delta mix G with respect to pressure, and I do that at a constant temperature. And so if you go and you look at, all right, the delta mix G that we had written down before, do you see any pressure there? And the answer is no, all right? So when you do this partial derivative, everything up in this delta mix G, when you look at the mathematical form, it's essentially a constant relative to this P, all right? Everything's set, right? We're keeping temperature set. That means that delta mix V is equal to 0, right? Now, this is an important thing because what we say in chemistry all the time is you can't assume volumes add. What does this tell us? Volumes do add, all right, for ideal solutions. Now, how does it tell us that? Remember what this indicates. This indicates, hey, what change in volume do you expect to see when you make the mixture, okay? So when I take a volume of our red dots and I take our volume of our blue dots and I put them together, this indicates what change in volume you expect to see through that mixture process. And guess what? If the solution is ideal, you should see 0 change in volume. The volumes become additive for ideal solutions. A very, very important result, all right? Again, all of this is predicated on the idea that we started with that mu that had the Raoult's law information in it, that was following Raoult's law, that weren't experiencing any deviations. Ideal solution behavior is what we're talking about, and I just want to stress that one more time, all right? The last thermodynamic quantity we're going to discuss now is we know delta V mix, we know delta S mix, we know delta G mix, all right? So what about delta H for the mixing process, all right? What's this equal to? Now for a fixed temperature and pressure, all right? Remember we have G is H minus Ts, dG is dH minus T ds minus S dt, all right? Where are we analyzing our mixtures? We're analyzing them under isobaric and isothermal conditions, right? So this goes away. So we have dG equals dH minus T ds, or dH equals dG plus T ds. And we can integrate both sides, remembering that we're doing, right, isothermal and isobaric conditions one more time. Delta H then is equal to delta G, right, plus T delta S, right? Now, why was I able to do this integration? Remember when I actually put the integrals here, if you can't kind of see what's happening, this T is isothermal. When you integrate a D, it turns into a delta, okay? So then if I want delta H mix, the enthalpy change, which is the heat, because remember we're doing this under an isobaric condition, so this is the heat of actually forming this mixture. What I need to know is delta G for the mixture. I need to know the temperature, right? And I need to know delta S for the mixture. Well, previous to this, we calculated this value, right? And we wrote it down, and you can go ahead and you can plug it in. And previous to this, we also calculated this value, and you can go ahead and plug it in there, right? Now, what we saw between those two, and I'll remind you real quickly, but I do want you to look at the math, was remember that this looked like delta G, but it was missing a T, and it changed sign, right? So make sure you can prove this, all right? But you have the functional form of that, you have the functional form of that, but what you see is that you should get 0 when you make those substitutions, right? So a really important idea here is for ideal mixtures, right? For mixtures where all the interactions are all the same between solute, solute, solvent, solvent, and solute, solvent, right? When all those mixtures are the same, what you expect to see is no heat to flow as I take my reds and my blues and I dump them together. As I make my binary mixture, I expect no heat to flow. And why is enthalpy heat in this situation? Again, remember, we're analyzing our solutions under isobaric conditions. So these are really important properties of ideal solutions that we need to know how to derive. But then again, we also have these formulas that we can use when we are given the amounts of components to be able to actually throw numbers into these and get a value for delta G and get a value for delta S. And then we always know what happens with delta V and delta H. Okay? What our next topic will be is what happens when our solutions don't follow Raoult's law. What happens when they're not ideal? We spend a lot of time looking at deviations. What do we do to approach these sorts of questions when we have non-ideal solutions?